Hello everyone, this is Ishani and Nandini. Distance Matters is our submission to the ENCMP 100 Programming Contest Fall 2020. The inspiration for this game comes from the story of the rabbit and the tortoise. Here, the player is the tortoise. To beat the rabbit, the player must find the shortest distance between the start and the end point on the map. There will be many routes to choose from. The player's task is to find the correct routes that add up to be the shortest distance to the endpoint. Let's have a look at the concepts used in this program. Each part or process of the game was assigned to a new user-defined function. We used built-in functions and learned how to modify its parameters to give us our desired outputs. Selection and loop statements were used throughout the code. We finally dived into object-oriented programming that includes creating plots, changing its properties, outputting text and images in figure windows, and also modifying their formats. We went through various versions of the code to finally reach the code that gave us the most favorable outcome.
Three major challenges that we faced while writing our code were implementing Dijkstra's algorithm in Matlab, plotting a graph, and creating a user-friendly environment.
Dijkstra's algorithm is an algorithm to find the shortest distance between nodes in a graph. Such algorithms are used in applications such as Google Earth or Google Maps. Let's look at this plot. Our starting point is S and we need to find distances to all other points. Initially, distances to all points are infinity, that is, they are unvisited. Now, distance to get to S will obviously be 0. Our unvisited node with the smallest distance is now S. Now we look at other unvisited nodes such as A and B. Distances to A and B change to 1 and 5 respectively as they are less than infinity. Now, our unvisited node with the shortest distance is A. A becomes our current node. From A, we look at C, D, and B. Distance to C changes to 3, distance to D changes to 2, and distance to B changes to 3. Now, we look at our shortest distance node again, that is D. From D, we look at C, E, and B. From D to B, our total distance would become 4. But B is already a distance of 3. Since 4 is greater than 3, it does not change. From D to C, our total distance becomes 5. But since C is already 3, it does not change. Now, distance to E would become 4. We see that distances from S to all other points are their shortest possible distances. Hence, Dijkstra's algorithm has solved its purpose.
In order to create our graph, we used an adjacency matrix. An adjacency matrix is a square matrix used to represent a finite graph. The elements of the matrix indicate whether pairs of vertices are adjacent or not. In this case, we used matrix for graph function to build our adjacency matrix depending on the level chosen by the user. In order to create the graph, we used our adjacency matrix and the inbuilt graph function in Matlab. While creating the graph, the two major difficulties we had to face were making sure that the graph did not have any self loops, and second, making sure that each node had an edge. In order to do that, we wrote a separate function, check for more than one edge, which checked whether or not each node had an edge. In order to make our game more interactive, we used various Matlab inbuilt functions, rectangle, text, etc. This slide shows an illustration of what we have done. So now that you've understood the background of our game, let's see how it's played.
Let's skip to the easy level here. As shown in the command window, our starting point is A. Using Dijkstra's algorithm, our points will be A to B, from B to G, from G to D, and from D to C.
Yay, so you won here. And now you're back to the main menu and you can further decide what you want to do.